Okay, let's introduce the passive element called inductor. And we see here, this is a typical inductor that you'll see in circuit elements. And what it is it's a passive element that stores energy and it's a magnetic field. Okay, it has applications in power supplies, transformers, radios, TVs, radars, and electric motors. So if you ever opened up even appliances, you open up your appliances or things, you might see coils wrapped around. In this case, you might have seen things like this guy in some of your appliances or your not electronics, but yeah, could be some of your electronics. These are typically your inductors. Okay, and any conductor has inductance, but the effect is typically enhanced by coiling up the wire, like we see in this guy. When you coil up the wire, you get coils in the wire. It enhances the inductance material. Okay, so let's go ahead and write this and then define some relationships. So, an inductor is a passive element that stores energy in its magnetic field. Okay. They have applications in power supplies, transformers, radios, TVs, radar, and electric motors. Okay. Any inductor or any conductor has inductance. But the effect is enhanced when we coil up the wire. The wire is coiled up. Okay. So we can further define this as an inductor consists of a coil of conducting wire. All right. If we allow current to pass through this inductor or an inductor, the voltage across it is going to be directly proportional to the time rate of change in current. Okay, so let's go ahead and write this down here. So if we would write this equation, V equals L di over dt. I'll define this equation here, and I'll define these in a second, the different components, but what this is telling us is if a current is passed through an inductor, the voltage across it is directly proportional to the time rate of change in current. Current. So that's what this is saying here. All right. Where we're going to define L is the unit of inductance. And it's going to be measured in henries. Or H. One Henry is 1 volt second per ampere. 1 volt second per ampere. The voltage developed tends to oppose a changing flow of current. Okay. So we can further define this is that inductance is a property whereby an inductor exhibits an opposition to the change of current flowing through it. Okay, and it's measured in henries. Okay, and the inductance itself is going to be dependent on its physical dimension and construction. All right, so just like we had with capacitance, we had area and the separation distance. Similarly, the physical construction of the inductor is going to determine the value of the inductance. So if you look at these, see if I can move this guy here. Let's undo. Take the lasso. Move these guys to the side. Okay, so if you look at these different types of inductors, and the first guy here, this is a solenoidal inductor. You see the shape is a little different than the second one, which is a toroidal inductor, and which is different than the third, which looks like a resistance there, is an axial lead. Okay, so these are different types of inductors. So again, the physical dimension and the construction is going to affect the inductance value. So if we look at the solenoid version of it, which is this guy up here, or the first one, so solenoidal, we can come up with L is equal to n squared mu times A over little l. So we'll keep this equation here with us, and let's define what these guys are. Okay, where n is going to be the number of turns, little l is the length, okay, A is the cross-sectional area. And then mu is going to be the permeability of the core. Okay, so if we look at this here, we're looking at our L, our cross-sectional area, the core permeability, and then the number of turns. So the core permeability is our mu. Right, so that's what we're looking at there. All right. And that permeability is going to be dependent on the material. And this permeability is a magnetic property. Okay, so permeability, this is magnetic property, okay, of the material that's going to be used. So let's go ahead and move this guy down a little bit, some more. And let's look at the current through an inductor. So let's look at the current voltage relationship. Current voltage relationship. Okay. So before we do that, let me just go ahead and get this out of the way. Let me define these guys. These are typical symbols for inductors, where we have the first one is a symbol for inductor with an air core. The second one is an iron core. Again, the core is going to affect the permeability, or the mu. And then the third one is a variable iron core. Okay, typical symbols for an inductor. Okay, let's come back and look at the current voltage relationship, which is obtained from looking at the change in current is equal to 1 over L times the voltage change in time. We can integrate this, and this will give us current is equal to 1 over L integral from minus infinity to some time t v tau d tau. Or we can rewrite this as I equals 1 over L T naught to T V tau d tau plus I T naught. So let's define this equation here. Highlight that. So what this is telling us is that we have a current voltage relationship like this. Okay. L is going to increase linearly here. So this is a voltage current relationship of this inductor here. So that's one equation we should keep in mind. And then we can look at the power delivered by the inductor. Or excuse me, to the inductor. And P equals VI, and we just substitute I that we defined in here, and skipping some steps, it's going to simplify to di over dt times I and then the current stored, or the energy stored, is going to be W equals 1/2 L times I squared. And we're going to skip the derivation of that, but just know that that's that relationship there. Okay, so a couple things to note is that the inductor acts like a short circuit to DC. Okay. And also that the current through an inductor cannot change instantaneously. Okay, so if we look here, current through an inductor cannot change instantaneously. Similarly, we had a similar situation where we're talking about capacitances. Okay, so if we look at this here, this is allowed. This is not possible. And then I'm going to go ahead and rewrite this. An inductor acts like a short circuit to DC. All right. And we're going to, just like we did with the capacitor, we assumed ideal capacitor. We're going to also assume an ideal conductor does not dissipate energy. Okay, so the energy stored in it can be retrieved at a later time. So let's go ahead and summarize. So this is a summary here of 2 points I want you to take away from inductor, but I'll go ahead and tell you that it does not dissipate energy stored in it if we're assuming an ideal conductor. And the energy stored will be returned to the circuit later. But of course, in reality, inductors do have internal resistance due to the wiring used to make them. So a real inductor has a winding resistance in series with it. There's also a small winding capacitance due to the closeness of the windings. And these two characteristics are typically small, though at high frequencies the capacitance may matter. Okay, so just some things to think about in real world inductors. But we're going to be assume ideal inductor. Okay. So that's just a quick introduction to the inductors and some equations to know. And go back up here.